Hello everybody. Welcome to our webinar today on NX Design for Additive Manufacturing, otherwise known as DfAM. I'm Bryan Fischer, your host. I'm an NX application engineer with Prolim out of the Cincinnati office. The webinar today will be recorded and it will be posted later on our Prolim channel, YouTube channel. On our agenda today, we'll be discussing what is DfAM, Design for Additive Manufacturing. We'll be converting a facet model into a convergent model, and we'll go over some DfAM design rule checks. Additionally, we will go into additive manufacturing with the build trade, nesting, and showing how to use automatic supports. The model that we will be using during this presentation continues on from my last webinar that was on topology optimization. If you had not watched or had not attended, you can always go to our YouTube channel, subscribe, and watch it from there. Here on our YouTube channel, you can subscribe here, and inside this information right here, if you type in NX and you do your search, you will see here that the video I recorded earlier this year. I would highly suggest that you go and subscribe if you have not done so. Videos such as this and lunch bites and what we call snack bites will also be released in here. You will get an update every time we go in and add in video. So what is Design for Additive Manufacturing? Design for Additive Manufacturing in NX is a set of tools and design rule checks such as overhead angle, wall thickness, and so on. This helps us addressing manufacturability concerns early in the design process. Additionally, it helps us with our print setup and looking into possible troubled areas with the design. As shown here in my example here, you see a conventional manufactured burner and an additive manufacturing adaptive burner. You can see the many ways that additive manufacturing can help a company save time and money. On a conventional manufactured burner there, it consists of 13 machined parts that were joined by 18 welds. With the additive manufacturing burner, we have one single part. You can also see that we had a thermal barrier coating on the front surface and an external pilot gas feed on a conventional manufactured burner. With the additive manufactured burner, we were able to optimize the cooling and we are possibly able to remove the TBC. Additionally, you will see also we saved on weight and lead time significantly. So as described earlier, we'll be using a model that I created using topology optimization in our last webinar. This model should look familiar to some, and for those that this does not look familiar to, this is an STL facet body that was created by using topology optimization. We'll be taking this topology optimized body, facet body, and we'll be converting it into what we call a convergent model. This convergent model allows us to use both reverse engineering and traditional modeling tools on the model. We will also go in and show how the automatic facet body cleanup is used and the areas that it can repair for you automatically. Now let's get into the demo portion of this webinar. I currently have open NX 1926, the latest continuous release here. And as you can see, I currently am showing a body here, lightweight body, facet body. This is the body that I obtained while using topology optimization. However, if I want to make some changes and stuff like that, I am limited right now with only being able to use the reverse engineering tools. However, if I go and make this a convergent body, it opens up more tools for me later on if I need to do modification. So you can see right now with this facet body, if I try to create a hole, and I pick my body here, you will see an alert down here in the bottom right that tells me it's not a valid body for that. To be able to do that, what we're going to do is we're going to go to my polygon modeling tab, and we're going to go up to convert facet body. The facet body type we want is a convergent body, as I stated. It's suitable for model and reverse engineering. Additionally, I'm going to leave the automatic cleanup on. I'm going to leave this at default right now, and I'm also going to keep the body facet body that I prior have for documentation reason, history reason, whatever. Go ahead and pick my body here, and I'm going to say OK. And now you can see over here in our modeling tree, we now have this new feature called convergent body, I'm sorry. And we also have the lightweight on top of it. I'm going to go ahead and hide the lightweight real quick. And I left the facet bodies there at 100 when I went and I converted it there. And if I come in here now and I say clean up facet body, the reason I did that is I wanted to show this clean up facet body tool. If I say all to analyze, pick my body and show results, you'll see that we have 200 degenerate facets and so on here. In the past, you would have to go in and manually clean this up as a user. However, now with this new tool, I can come in here and say all to repair. Go ahead and show the results here. And once it's done, you'll see that it cleans up the body, and I no longer have any of those degenerate facets and so on. So I'm going to go ahead and say OK to this. This now allows me to use, like I was saying, both traditional modeling and reverse engineering tools. However, for today's webinar, we will be focusing on the design for additive manufacturing and be doing very little of the modifications. However, I do want to go in there and do a couple little things such as hollow or shell. And this is due to one of the checks that I'm going to be using when we are in the design for additive, and I'll mention that when we get to that. So now we have a shelled body. And now we can get into our design for additive manufacturing portion of our webinar. So we went in and we were able to take that topology optimized body, also known as the Generative Design, and we went in, we converted it over to a convergent body, and now we're going to go in and we did the automatic facet cleanup. And the next step is for us to go in and start looking at some of these DfAM tools, such as overhead angle, wall thickness, minimum radii, wholly enclosed volume, and so on. So let's go ahead and jump back into NX, and we will start looking at some of those features now. Now back in NX, let's go ahead and look at the Design for Additive Manufacturing tab. As you see, this tab is broken into 3 sections: base, validate, and lattice up there at the top. We will not be focusing on lattice for this particular webinar. That will be saved for a later date. But we are going to get into some of these validation tools and also the base area there. So let's go ahead first and look at our parentheses here. For those individuals that are not familiar with parentheses is and information you may need, you always can come up here and hit the little help icon, or you can hit F1 on your keyboard, and it will actually come in here and give you information on what parentheses dialog box is. Or we could come in here and look at parentheses here, and it explains to you that the part would rest on the XY plane and your build direction would be in line with the Z direction. So we have the ability to change that, and we also have the ability here to still go ahead and we could go user defined, and if I pick my body and I come down to my CSIS here, you see a dynamic CSIS that we're able to change. Or I could come up here, reset my dialog real quick, do a minimum height, select my body, and say OK. Now if I rotate my part, what you'll notice is we will be sitting directly on the XY plane there. That's where your build plane would be, and you'd be in the Z direction. So that's one way that you can get your parentheses. Now we're going to move on now and start looking at some of these validation tools, and we can also reset the parentheses from those validation tools. So the first validation tool we want to look at is the overhead angle. The overhead angle here allows us to go in and look at the overhead angle, which would be used mostly to see how much support's needed for when you're printing your part. So I'm going to go ahead and select my body here, and I currently have my overhead angle at 30 and 35 degrees is the extended angular tolerance. As you can see, it's color coded right now. Anything in the green would be the maximum overhead angle, less than the maximum overhead angle. Anything in the yellow is more than the overhead angle, but within that tolerance. And anything in red is the area that we would need support. So if I go ahead and rotate this part here, you'll notice on the back side, we have a lot of red there. That's where we would need our support. And the yellow is the area that you may or may not need your support, depending on some criteria, such as your printer, material, and so on. Now we do have the ability to come in here also and create another parenthesis. And I also have the ability to come in here and say specified build plane. And we have a dynamic thesis that I'm able to go and drag and pull and stuff like that. So if I come in here now, for example, and I'm going to go ahead and rotate to the z-axis here, and you'll notice that we get a change in the area. If I go ahead and rotate the axis again, this is changing, you know, what direction we'd be printing. And you see there we're now down to 94.33. So these are the areas here in the red that I would have to put some support. Now if we decided that this is the biggest criteria, that this is what we want, and I want to come in here and create another thesis, I come in here and say create print thesis. And what occurs is the last print thesis now becomes a regular thesis. So you'll be able to say okay here. I'm going to go ahead okay this real quick. And then we're going to come over here in my part navigator here, and you'll notice we have the original print thesis is now just a regular datum coordinate system, and the one I just saved becomes my new thesis. And if I rotate that part again and we look at it, you'll see that the bottom of that part is sitting on the XY plane, and now our Z direction is our new print thesis, and we'd be printing it in this manner. So these tools that I'll be going over here with throughout this section, you'll notice that we're able to go in and actually change these print theses depending on if we like that criteria or if we don't like it. So we can always go in and change it back to the other thesis, such as this one here, later on if we choose that as more of a driving force for what we need. Now anytime you run one of these validations, you can always come back to those validations too. If we come back over here to our HD 3D tools, you'll notice that we have this now little plus sign here, and we can always go back into that overhead angle validation that we did. I'm going to go ahead and cancel this one, and if you had this turned off by deactivating it, you'll notice when you're in your HD 3D tools, you now see this little eyeball here next to Additive Manufacturing, which tells us that there is validation within there. So if we come over and we double click on this again, it reactivates those validations. I'm going to go ahead and deactivate those again, and we'll go ahead and look at the wall thickness validation next. I'm going to deactivate that. We're going to come over and I'm going to hit wall thickness. And now when I go into here, you'll notice that we have the still same specified build plane that we can always change if we want. And we do have a minimum wall thickness here. And if it's in green, it would be more than the minimum thickness. And if it's in red, it's less than the minimum thickness. I'm going to go ahead and turn this off and go ahead and shade this real quick. And turn on our preview. And you'll see it goes through the analysis there when I turn on the preview. And anything in the green is now an area that is greater than the minimum wall thickness. If we go ahead and turn this back on, anything that's red will show up, and we should be able to see if there's any areas of concern there. There looks like there's a couple low areas here. That's mostly probably because it's a facet that we may have to clean up later, but we're not going to concentrate that on today. We're going to concentrate more on how to set this up, the validations we can run and things like that. And later on a later webinar, we will get into some of those reverse engineering tools and some of the other tools to go in and actually clean up these convergent models. So I'm going to go ahead and OK this one, and we're going to leave the parentheses as that is. We could always change it, like I said, if we decide that the wall thickness is a greater criteria than the overhead angle. It all depends on what your design is, like I said, along with some of your other requirements, material, and such. Let's go ahead and look at a few more of these validation here. Let's go ahead and look at minimum radii. The minimum radii, much like the other validations we've been using, have a green and red color code here. You can also show less and more depending on, you turn it off and on, you get your color code. If you turn it back on, you only see the red areas. These areas can be cleaned up, like I said, but we will not be concentrating on that. You also have a display resolution, so you can display it extra fine, super fine, and so on, so you can make the resolution different. I'm going to go ahead and OK this one. And you'll notice it just keeps on adding these different validations again over here on the left-hand side under your HD 3D tools. The next one after that we want to look at is the print volume. So you can see here when I come in here, I'm going to go ahead and fit that real quick. And you'll see the blue there. That's actually our print volume. In this case right now it's set to custom. But if I pull that custom down, we do have some other printers that I have loaded in here. So I go ahead and pick that one there, and you'll notice that we can now see the print volume. The volume display, we can have both printer or product. So as I change this, you'll see that we change the different things in there. Because I have it on automatic update and preview, if it's inside there, it'd be green. If the body was close to the printer boundary, it'd be yellow, and red would exceed it. So this allows us to go in there and actually set up the part and make sure we're within a print volume prior to sending it off to actually being manufactured. I'll go ahead and OK that one also. I'm going to go ahead and say fit on this, get us fit back in there. And then we'll get through a few more of them, and then we'll start onto the actual manufacturing side. So the next tools that we're going to look to are under the more here. We're going to look at the wholly enclosed volume. So where this is important is if you have a hollow body such as we have now, and you're using a powder bed, you would have powder trapped inside there. It has no way to escape. As you can see right now, my part is completely red because I have no area that the powder would be able to escape. I'm going to cancel this, go back over to my home directory, and I'm actually going to blow a hole in here real quick. Come in here, and I'm going to pick it here and go ahead and say OK. Notice it's going back and it's actually calculating some of the information also for these particular validations. So I'm going to come back over here now, Design for Additive Manufacturing, come back over to my wholly enclosed volume, and this time when I pick it, you notice it chooses the body right away. There's no red because now I have an area that the powder would be able to escape. This is an important check for when you're using a powder base. Now, in this case, it's a simpler model. We know it's hollow, but if you had a more of a complex model, you may have an enclosed area and not know it. Now, these checks here that I've done, these were all manual checks. However, we do have a part orientation. This part orientation actually takes several different checks and runs it for you. This is more of a wizard here. As you can see here, my print, I have different ones there. I have a powder bed fusion, multi-jet fusion, so on. And for this particular one, I'm going to go ahead and say powder bed. And you'll notice if I go to next, I have certain checks there. And if I went back up the printer and I change that to a different printer, you'll see that we have different checks. So this depends on your printer and what your printer's capabilities are and such. So I'll leave mine though on a powdered bed, and I'm going to go ahead and leave all these checked, including overheating. Many of these checks again can be done by manually doing them, or you can actually utilize this part orientation. So next, I'll hit next again. We'll come over here, support volume parameters. We can change that if we want. I'm going to leave it as it is in default. Same here with the print time. I'm going to leave as default. You could change this depending on your printer. Overheat, I'm going to leave that as default also. And we're going to go and select orientation. I'm going to leave where we're at. So first thing that comes up, it tells us right now what our surface area is, our support volume, print time, and overheat. Next, when I go to optimize this, I'm going to leave it on low right now. I could put that up higher. It would take a little bit longer to calculate, but you get a little bit different results. And I'm going to come over here and say start calculations. This will give me 10 different orientations. So as we wait on this, it goes through all those checks and gives us different options. So right now this is our actual as we currently are in our print seasons, but we have the ability to do multiple different orientations once we have this run through. Okay, now that it's run through all the way and done all the calculations, you can see now it changes to a min, actual, and max. It gives us a little chart here that we can look at, gives us information here. I'm going to go ahead and say next here, and what you'll notice is I can turn off any of these if I choose now also, and I could also change the weighting of each one. So if I come in here now and I choose one, you notice it gives us information there. And then what you'll see, it gives us the area, the volume, the print time, and overheat. And once again, this comes down to what the individual wants, what criteria are set in place, what printer you have, what material. This is going to be dependent on the user, but it gives you these different options, and you can quickly see where the print thesis would be. You can see the direction it would be. If I change this to number 2, you see it takes these different weights into consideration, and you'll see also these numbers do change, and it gives you a little chart here where it's at on from min to max. So you have the ability to go run through all these and figure out what makes sense for your company, your machine, and your criteria. Once again, once you have this done, you can offset from the build plate, and you also have the ability to go and create the print thesis from here. I'm going to leave our print thesis as it was prior, but I'm going to finish this out and just say okay. And now it is in the validation also. So you have the ability to come back over here and change to that if you choose so at a later time. So that goes through most of the tools right now for design for additive manufacturing. We will be creating another part file here soon, and we will be putting this into the manufacturing environment. But before I do that, I want to make sure I come in here, and I'm actually going to create a reference set just for this body. So my construction geometry that I used earlier when I used Topology Optimization to create this body is not going to be in that reference set, and will make it a little bit easier for us when we go on the manufacturing side. We're going to go ahead and save this also real quick. And our next step will be to go in and actually start and create that manufacturing part. I'd like to thank everybody for attending today. That concludes our webinar today. This will be a series of webinars that I will be releasing at a later date that will include the manufacturing side, which will include the build tray, nesting, and the automatic supports. If you have any questions at this time, please let me know and we can go ahead and answer those questions. You can also contact me here on the information that you see on here, such as brian.fischer@prolim.com. And you can also go and visit our YouTube channel also. Once again, thank you, and I will be taking questions now.